So we can start with this simulation. You can download this file and you can play with this photoelectric effect simulations. Okay, so you'll see that you'll get complete informations about the photoelectric effect in this simulation, and you can play here. You can change the frequency of the incident light, and you can also change the applied source voltage over here. Okay, so you can change both of these. Based on that, you can see like how much photoelectric current passing through in the circuit for a given value of the applied um, uh, uh, given value of the applied frequency. Okay, you can play with that. So next, move forward with the momentum of a photon. Okay, so the momentum of a photon, we have to be careful that the rest mass of the photon is 0. So photon don't have any rest mass, because if you consider the relativistic mass, so we know from the previous chapter that mass in the photon in the relativity, we know m equals m naught under square root of 1 over v squared over c squared. So we know that this m is the mass of an object, when mass of an object when its speed is v. Okay, so this is the case of relativity, so we call it the relativistic mass. So now, because in the case of photon, we don't have the rest mass, so m naught is called the rest mass of this particle. Okay, so for the case of photon, we have to consider it as a relativistic particle, photon. So under that thing, we have to say that momentum of a photon, say we represent by symbol p, it will be E over c. Okay, so E is the energy of photon, E is the energy of the photon. Okay, so this energy we can write as H times F over C. Okay, so again we can simplify H over F over C is the lambda. Okay, because we know that this lambda, because C equals F lambda, that means if you want to find F over C, if I divide both sides by C, then we get that implies 1 equals F over C times lambda. Okay, so we can write as 1 over lambda equals F over C. So we can use this concept to get that result. Okay, so this is the these are the equations we are generally using in the case of photon. Okay, but if a particle has mass, then we have to use m equals m naught over under square root v squared over c squared, and then we can write the so we can write the momentum of the particle as p equals m times p. Okay, but this is true if they have mass, but we don't have mass in terms of the rest mass for the photon. We have this equation will be true. Okay, so let's move towards the other the application of this phenomenon. Let's first we see if this is the X-ray. X-ray is basically the inverse of photoelectric effect. Photoelectric effect. Okay. So if you remember, in photoelectric effect, this is the metal. Okay. We incident here the electromagnetic wave of frequency, say F. So this is the electromagnetic frequency or light. Then we know that it interacts with electron here, one electrons. This is the electron. Okay, it interacts, and then this electrons comes out. This electrons is out with a speed v max. Then we have the relation is HF equals half mp squared maximum plus p value. Okay, this is the result in the case of the in the case of the photoelectric effect. Okay, so just reverse phenomenon we could expect here. What that means, if we have a beam of electron. So again, we are saying that this is a metal, same metal or different metal. Then we are going to hit with the fast moving electrons. Okay, so beam of electrons. So beam of electrons striking on the metal surface. So after we'll find that the electromagnetic wave will comes out from this metal. Okay, so electromagnetic wave we get electromagnetic wave. Okay, so this is just the reverse phenomenon. Reverse means in terms of inverse phenomenon of the photoelectric effect. Okay, so this phenomena can be explained in some ways. Okay, so just this is the this is one of the approach to explain how we can get this X-ray. So if you see in the picture over here, you see that this in the picture, we see that this is the filament get heated. This is the filament. This is heated by a battery. If you heat, electrons will comes out. Okay, electrons is out. So these are the electrons. These are the electrons. These are the electrons due to heating. Due to we can say electrons out from metal due to heating. Okay, it happens like this. So to speed up, we have to join. We have to join with the potential difference. So this just you see in this picture, we have to join one with the battery positive, other with the battery negative. So we'll do this battery positive here and battery negative goes here in the system. Okay, we are going to hit here. Then this beam of electrons is because of this potential difference, we can also call it, they are called the accelerating potential difference. Because of that, these electrons get speed up and speed up. Okay, so these electrons get a speed up and they could hit this plate, middle plate. After that, when fast moving electrons and fast moving electrons, so we'll come to this point later, but this is also called the cathode rays, but they are not rays basically. Actually not rays. Okay, but we call it cathode rays. Okay, so fast moving electrons hit the metal and we get X-ray. Okay, X-ray means this is the electromagnetic wave. Electromagnetic wave. So how the X-ray are produced can be explained in two ways. So I'm just going to explain one of these. Okay, so I could say this is the production of X-rays. I would say X-rays. So just say we have atom. Okay, this is atom. So here I represent this as a nucleus. In nucleus, you know that we have protons and we have neutrons. Okay, and electrons are orbiting in different orbits. Say this is the first orbit, this is second orbit, maybe third orbit. Okay, so you know from maybe in the chemistry, this n is equal to 1 first orbit is also called K. This is n is equal to 2, and this is n is equal to 2 orbit is called L. This is the n is equal to 3. This orbit is called KLM. Okay, so you know that electrons in each orbit depends on, in general, it follows the 2n square rule in general. Okay, so first orbit may have 2 electrons, second orbit may have 8 electrons moving around this center. Okay, so say for example we have 2 electrons over here. Say then what it does, what could be possible that this high speed electron can hit that electrons. Okay, so we have this electron with high speed, this high speed electron from outside hit that electrons, and because of that, what will happen, this electron will go to the higher energy level. So in this case, this energy is going to increase in that sequence. So energy, high energies. Okay, so energy of first orbit is least, energy of second energy is higher, energy of third orbit is going to be higher. Okay, so because of that, when it hits, this electron comes out from this here. Maybe this electron jumps somewhere in higher orbit, say here. Okay, so once this electrons went back to its position, then this X-ray is produced. Okay, so this high speed electron from outside hits this electron, and electrons comes out, and when the electron went back releasing energy, then in this case, this energy could be X-rays could be produced. Okay. So let's see here one more time. Say, just consider, for example, for simplicity, just consider 2 orbits. This is the nucleus. So this is the orbit. It has energy, say E1. The second orbit, or maybe the higher energy level orbit, so E2. So just say that E1 is the low energy level, low energy level, and E2 is the high energy level. Okay, so if an electron jumps from high energy level to low energy level to high energy level, we need energy. When it going back, it actually release the energy. So we can write change in energy between two orbits is equals to h times f. So basically this change in energy is E2 minus E1 or times hf. Okay, so we can say that this here this E2 minus E1 over h times c over lambda. So this is the energy released in the form of X-ray. So this would be the energy of X-ray produced. Okay, so in our case, we can use the same equation that we used before, that if let me write somewhere, if V is the potential difference between anode and cathode, okay, just like here, in the more defined picture over here, if V is the potential difference between anode and cathode, then we can write E times P, okay, this is the work, which should be equals to energy of photon. So we know that HF. Okay, so F is the highest value, maximum, or EV, we can write H. If C is maximum, F is maximum, lambda will be minimum. We can use this equation to see, to use to find to find the quantities like P. Okay, so V is the potential difference between anode and cathode in the picture. So this F maximum is the maximum frequency of the emitted X-ray. So F maximum is the maximum energy, sorry, maximum frequency of emitted X-rays. Okay, we'll talk about more about this energy emission in Bohr's law. Bohr's postulate. Bohr's postulate. Bohr's postulates. So we'll come to this point later. So this is all about the X-ray. So let's go further about the Compton effect. So in Compton effect, so we have say in Compton effect, say for example, we have, say I'm doing there at first, say axis. This is my x-axis, okay, and this is my y-axis. Okay, just for simplicity, say I have one electron at rest. It's the electron. Okay, so this is the electron over here, and this is the electron. Okay, so this is the electron at rest, for example. It is hit by an electromagnetic wave. Okay, so we incident electromagnetic wave, or we can say light, having with photon energy S times F. Okay, then this energy is shared with this electron, and what will happen is that this electron will scatter around, say scattered along these same electrons. Okay, this is the electron. After heating by a photon, and this actual photon is also going to deflect, say in this going, say for example, going in some the other way around, but making an angle, say theta. Okay. The difference is that now after hitting the electron, it's say for example, it has initial wavelength is lambda. Now after hitting that, its new wavelength gets changed. Say now new wavelength will be lambda prime, say for example. Okay, we can say that it is the lambda prime. So we can do some math. So after doing some math, we'll figure out that change in lambda value, lambda prime minus lambda, equals H, if this is the case of electron, me times c over times 1 minus cosine theta. Okay, so in this picture, I would say that lambda is the initial wavelength of photon, Okay, this lambda prime is the wavelength after scattering. Okay, and for the electron, we can say that me is the rest mass of electron. Rest mass of electron. Okay, so this angle theta is called the scattering angle. Scattering angle. Theta is the scattering angle. Okay, so the term for the electrons, we consider this part H over me times c. This is called it has a name, it's called the Compton wavelength. Okay, so if you plug the value of H, m, and mass of electron, and the value of c is the speed of c is the speed of light in air. If you plug all those numbers, this comes to be close to 2.43 times 10 power minus 12 meter. It comes to be around that. Okay, so you know that, but change the shifting wavelength depends on angle theta. So we can use this equation to find the shift in the case of to find the shift in the electrons. Okay, so the main question is, what is difference between Compton effect and the photoelectric effect? Okay, so just think that how we can say the difference between photoelectric effect and Compton effect. because both actually explain this, both phenomenon basically explains the quantum effect. So both are explaining the both are the example of the quantum effect. Both explains the quantum effect. Quantum effect. This cannot be explained by the classical physics. Okay, so if you see in photoelectric effect, in photoelectric effect, you already see that electrons are bonded to the bonded in a metal surface. Okay, metal surface. But if you consider the Compton effect, in the case of Compton effect, you see that in Compton effect, the electron is free electron. The electron is free electron. It's not actually bound to a surface. Okay, so this is the experimental setup to study the Compton effect. This is the source of X-ray. Means this gives the value of lambda. This lambda is the initial. After scattering, its wavelength is this much. This is a kind of final. After scattering, this electron is, it could be here. Electron could deflect in some way, just like we showed here. Okay, this electron could deflect anywhere. So the point is here that photon wavelength gets changed when it hits it's not only on electrons, it can hit any particles. So this is the interactions. This is the example of interaction between photon and particle. It could be electron or it could be anything else. Okay, so let's move forward and see. So these are the examples for different angles. Okay, if your angle is 0 degree, then lambda and lambda prime, or what symbol did I use here? Lambda prime, yeah, that's same thing. It will not change. They are same thing. But if there is an angular deflection is 45 degree, in that case, your change or shift, which is equivalent to lambda prime minus lambda, is this one. If your angle theta is 90 degree, your shift in the wavelength, which is lambda prime minus lambda, will be that one. So it will keep changing. Okay. So if you understand up to this point, you can solve this problem, practice 2. Okay. So here, this is from the X-ray. So in the X-ray photon, the electrons are accelerated. So through a potential difference of 55 kilovolt. Okay, then you can find what is the maximum energy in the photon electrons. Okay, so this is the another example of the effect of the quantum phenomenon. So in this case, is called the pair production. So we are talking about matter and antimatters. So in this case, for example, electron and a positrons, they have they have same mass, but its charge is, positron charge is E plus and electron charge is E minus. So this means it's basically 1.6, 10 minus negative 19 coulomb. This should be minus 1.6, 10 negative 19 coulomb. Okay, but they have the same mass. So this means, now this means a photon, say this photon of energy, total energy, this one's HF, it would produce the pair production. We call it pair production. This means this energy gets converted into mass. So one part it goes as electron, and other part it will form as the one will be the electron, other is the positron. Okay, so this kind of phenomenon is called the pair production. Other quantum effect is the Heisenberg uncertainty principle. It says that in the quantum mechanics or in the quantum physics, we cannot locate anything exactly. Okay, so for example, if we know everything about where the particle is, then we don't know its momentum with 100% certainty. Okay, so this telling you the idea is that if the uncertainty in position is delta x and uncertainty in the momentum is delta p, it will be greater than or equal to h/2. So here delta x represents the uncertainty in position, and delta p represents the uncertainty in momentum. So we cannot figure out both quantities exactly at the same time. Okay, so this is called the Heisenberg uncertainty principle. So this is one of the key principles of the mechanics. It's called the quantum mechanics. Similarly, if delta E is the uncertainty energy and the delta T is the uncertainty in time, then we can write the product of delta E times delta T will be greater than equal to h/2. Okay. Then other phenomenon we talk about here is the wave particle duality. Means wave and particle phenomenon are dual. Sometimes particles behaves as a wave, and wave also behaves as a particle. So they are related by the wavelength we call the de Broglie wavelength. So this lambda is equal to h over p. P is here is the momentum. So we can write lambda equals h over mv, mass times velocity. Okay, this is the de Broglie wavelength. So they relate the two phenomena. They relate wave phenomena and we can say they relate the wave phenomena and the particle phenomena. But if we are talking about photon, because photon has the rest mass 0, no rest mass. Okay, so the photon. So for the photon, we can write the following equation we wrote before. Okay, so for the photon, momentum will be related as lambda equals h over p, which can be written as like this. We can be written as like this: P equals energy over C, and energy is equals to S times here. So we get this equation from the relativity. Okay, relativistic particles. So we have to combine these three equations in the case of photon. So let's move further and see what is left. So if you understand up to this point, you can solve this problem. So it has two parts, one for the electrons and other for a bowling ball. So you can find you can determine the minimum uncertainty in position. So it means we want to find uncertainty in position for both cases, but they give you the uncertainty in velocity. So they gives you uncertainty in v. Okay, this is given. So this is the uncertainty in velocity. Okay, so you can use the equations above, equation given before to solve this problem. So there are a lot of beautiful examples of the quantum mechanics. So you can find a lot of in the applications. So you can find a lot of application of quantum phenomena. Okay, quantum phenomena. So just quantum phenomena, it could be photoelectric effect. Okay, we can use the application of the X-rays. Even we can use the other quantum phenomena. Here are some of the link. You can use a lot of video, a lot of lectures you can find under UCI Open, and these are some of the resources you can use if you want. Okay,